Hi, I'm Husky. For the last 2 months, I've been working on an indie MMO called Lightless using a custom game engine I built myself over the last 4 years. If you're interested in some of the other aspects of this process, I've left a link to a playlist of my other devlogs below. But today I want to talk about something important regarding the development of a game like this: player count. Specifically, the first two M's in MMO stand for massively multiplayer, and if we truly mean massive, then we need to prepare for a lot of players in the same world. Now, I can't possibly say with any certainty how many players will play this game on launch. For all I know, it could be 1 to 10, 100, 1,000, who knows. The important factor here is this. Let's say that we plan for only 10 people to be playing this game on launch, and as such, we design our servers to only be able to hold 10 players at a stable performance. Then on release, 100 people try to play, and suddenly we're either only letting 10 people of those play at a time, or all 100 are trying to use a single server, leading to degraded performance for all of them. This introduces a slightly annoying issue. We have to plan in advance for the maximum amount of players possible, and that maximum can't be the amount of players we realistically expect to play the game. It has to be the absolute worst case scenario of this game completely blowing up with higher player counts than we can imagine. It's very important that we make sure that this game works well for everyone on launch, because if it doesn't, there's a chance it'll work for pretty much no one at all. Now, theoretically, we could just buy a really expensive, super powerful server to run the game on, and that might solve our issues, but that comes with a different issue: risk. If we buy an expensive theoretical server capable of hosting 1 million players and then only 10 players ever join, we've just wasted a ton of money, which as indie developers, we don't have a lot of. Ultimately, I think this is a very big reason as to why independent developers, or developers in general, don't make MMOs very often. It's sort of high risk, medium reward. But what if we took a different approach? Instead of buying a super expensive server to host 1 million players, we bought a couple of cheap servers capable of hosting 100 players. And what if we designed things in a way where we could just buy more of these servers if the game grew bigger? This is the solution I want to go with for my game, as it shifts the burden from cost to development time, which, at least at the moment, I have way more ability to spend. Now, you might be looking at this idea and thinking, yeah, that's super obvious. Just host multiple small game servers. Pretty much every small multiplayer game with centralized servers does that. However, while this is one technique I will be using, there's something we can do additionally that comes with a couple benefits. What if I said we could use this method of buying multiple cheap servers, but also have thousands of players in the same world, all seamlessly without any obvious loading screen transitions or server selectors? For the last week, I've been working on a system to solve this issue, and that's what I'll be talking about today: seamless high player count support. Now, for the people who enjoy the very technical aspects of stuff like this, I should note that a lot of the design for my system was inspired by this paper that I've left a link to in the description. But otherwise, this is the system I've created: the Lightless Architecture for Multi-Server Zoning, also known as LAMS, and as of today, I've made it fully open source and released the source code on our Git server. It's designed to be very agnostic towards both your game's internal structures as well as what connection method you're using between servers and clients, although it does come with the requirement that you manage clients and entities using its own system. To describe how it works, first I'll describe the exact problem it's designed to solve. Say we have a player in a world, and we want to separate that world into multiple zones, each of which should be mainly ran on a different server. That means that each zone handles packets and NPC interactions only for players and NPCs that are physically within that zone. Since each server only cares about stuff that happens in its own zone, that means that the server doesn't have to do anything with any amount of players in any other zone, and to that server, the performance impact is essentially equal to if there really only were the players in that zone. Now, this is all well and good, but this only works if nothing ever moves. What I mean by that is, what happens when a player leaves the zone that the server owns? If you picture how a typical client-server connection looks, we're kind of stuck with being connected to the server that we're first connected to. And as such, if we leave the zone that the server owns, then we have to figure out some way to reconnect to the new server for the new zone. Meanwhile, we also have another issue. Let's say we have a player in Zone A and a player in Zone B. These zones are physically right next to each other, but because each player is in a separate zone, they can't see each other. This is very much not seamless, and in practice would give off a very empty feeling to the world. Furthermore, this means that if an enemy NPC crosses the line between zones, we can no longer attack or interact with them, which in practice would definitely feel very janky. Luckily, we can solve both problems with a very simple concept, which is something I've called secondary zones. Basically, each server has a primary zone, which is the zone that it manages and does calculations for, as well as a number of secondary zones. These secondary zones are a list of zone IDs, and the server containing the primary zone will actually establish a connection to each of the secondary zones, and they all share information between each other about what's going on in their own zones. The client also establishes a connection to not only its own zone, but all of the secondary zones as well, and uses that for two purposes. First of all, this means we'll be getting all the information from the secondary zones, which allows us to actually see what's going on in them. But more importantly, since we already have a connection to them, when we move to a new zone, the servers just automatically know which connection is to the new primary zone, and all we have to do is connect to the new secondary zones and disconnect from any zones that don't matter anymore. In practice, we also have to handle the edge cases of teleporting between zones that aren't in the list of secondary zones, but with all this handled, we now have a theoretical system that solves all of our problems. Despite that, we still have to actually implement it, which involves not only implementing the system manager, which as I said before is available in the description, but also rewriting basically all of the server code to support this new system. I'm writing this after having done all of that, and while implementing the system manager took maybe 1 to 2 days initially, actually rewriting the server code to support it took pretty much the entire week. To put into perspective how much work that was, I did all of this on a separate Git branch, and when I made the merge commit, it was about 7,000 lines added, and this was before I started bug testing. Speaking of bug testing, that's the main issue with this system: extreme complexity. Previously, we just had to worry about running synchronous server code, which, don't get me wrong, can be very complicated, but now we have to worry about synchronizing the results of that code between not just multiple threads, but multiple servers. Multi-threaded synchronization has a lot of nice quality of life things that makes it way easier than multi-server synchronization, that mainly being based on shared memory. But when we're using multiple servers, we can't take advantage of stuff like atomic numbers or mutexes and have to structure everything around passing messages over the internet. I've actually come up with a pretty good solution to this though, which is the event system. In theory, every time we want to have two entities interact, we can simply pass events between them, and this should allow them to seamlessly interact regardless of what zone they're in. In practice though, this is even better, since we can specifically filter events to only go to certain servers and clients, which gives us a ton of control over the entire distributed system. And since each server is connected in a web-like fashion, we could theoretically make sure a message ends up at the exact server containing a given entity or player, and no matter what, it'll just work. However, while this all seemingly worked very well on both my computer and other computers on my local network, a problem arose very quickly once I started privately playtesting with some friends. A couple of my friends specifically don't have the best internet connections. I personally have gigabit Ethernet connections to almost every computer in my house, but that's very unrealistic to expect from the average player, and notably, some of my friends are just using laptops with Wi-Fi connections. And this resulted in a very odd bug in the first playtest. Seemingly out of nowhere, connections were either just disconnecting or dropping packets, and this only seemed to happen when the connection to the server was very poor. Now, some of this was specifically my fault, and had to do with some bugs I'd introduced into the system that handled keeping track of connections to servers. But even after fixing this, there was still a very high chance of bad connections just dropping regardless of what I did. I'm using TCP for client-to-server connections, and theoretically it should prevent anything weird from going on with the packets, and I also specifically haven't implemented any connection timeouts, so there theoretically shouldn't be any reason for the connections randomly dropping. And after a couple hours of obsessively reading Wireshark dumps, looking at the Wikipedia pages for networking layers, and testing the game on a laptop connected to a Wi-Fi network in another building for an authentic bad connection, I finally figured it out. Apparently, many firewalls seem to forcefully disconnect TCP connections if nothing's happening on them, and the solution to this is to just send empty packets over the connection at a fixed rate to make sure nothing thinks the connection is dead. Now, I originally thought that the TCP Keep Alive was implemented on the TCP layer, and as such didn't need to be implemented on the application layer, and I was actually correct. However, the TCP Keep Alive feature is optional and disabled by default, and because the Rust standard library doesn't expose TCP Keep Alive options, I have to implement this on the application layer. Luckily, this is incredibly simple. I literally just spawn an extra thread on the server that sends Keep Alive packets at a fixed rate until it detects that the connection is closed, and then exits the thread. However, this is a very annoying thing to have not known of before, and just maybe if I encounter 10 more of these annoying networking things, I'll consider switching my game networking stack to UDP. Despite all this work I've done, unfortunately this means that I spent around a week of work with basically no visible changes to what the game looks or plays like. I mean, you can see your hands, or I guess paws, holding items now, but that's about it. Nevertheless, I've been working very hard in the background on planning not just some big additions to the game, but also the first public playtest, which me and my friends have been attempting to prepare for quite some time. I still can't say when it'll happen, especially as I want the game to make a good first impression, but I very much want it to happen relatively soon, and I'm very excited for when it does. That's about it for today. Discord server and donations page are in the descriptions as always. Donations are not required, but very much appreciated. Okay, bye.